Hi, I'm Martin Swetman, and in this video I'm going to continue my review of the Younger Dryas impact debate research. And so far we've covered the published research from the original Firestone et al. Paper in 2007 through to the middle of 2014 in the last video. And in this video I'm going to finish off the papers from 2014, and there's only two of them. So remember where we got to last time, geochemical evidence for the Younger Dryas impact around 12,800 years ago has been found at nearly 30 sites across the North American continent, like this one at Murray Springs, and into Western Europe and the Near East by the Comet Research Group. And specifically they are found in this boundary layer at the base of the black mat, things like nanodiamonds, iridium-rich magnetic grains, and impact-generated spherules. And each signal has been confirmed by several independent research groups. That's crucial. Moreover, a platinum spike has been found in the Greenland ice that dates to within a few years of the onset of the Younger Dryas cooling, indicating very strongly cosmic impact caused the cooling. And probably the same platinum signal has also been found in Russian lake sediments. And more nanodiamonds and evidence of wildfires at around the same time have also been found in the Greenland ice, although those results have not yet been reproduced by other groups. It's important to note, though, that so far only about 7 or 8 of these Younger Dryas boundary layers, which are typically at the base of a black mat, are well dated to the beginning of the Younger Dryas period, about 12,800 years ago. Most of the other sites, and there are about 20 other sites or so, don't have such precise age depth models or don't have them at all. Nevertheless, these 7 or 8 sites span 3 continents, which means that so far everything is consistent with the Comet Research Group's claim of a single massive impact event caused by a swarm of comet debris spread out across perhaps an entire hemisphere of the Earth. Now our next paper is another one involving Isabel Israel Alcantara, but this time without other members of the Comet Research Group. If you remember, she had previously published a paper with the Comet Research Group claiming to find the Younger Dryas black mat in the sediments of a lake in Mexico, but the age depth model for that site was compromised, so we had to ignore it. Well, in this new paper from 2014, with some of her colleagues, she essentially repeats this exercise for a different site in Mexico. In this case, the site is well known for its collection of mammoth bones, which I'll just find for you. Here we go. Now this is a nice illustration of the site. This is a cross-section of a channel in which these mammoth bones have been found. So you can see all the different sediment layers at the edge of the channel here. And this channel is filled by a volcanic mud flow, which is known as a lahar. So the channel here cuts through the sediment with all its different layers. And this is a more detailed view of the edge of this channel here. And they identify lots of different sedimentary layers, and crucially they identify what they call a dark meteoric layer here. And it's sandwiched between 2 volcanic ash layers, one above and one below, and they know more or less the ages of these volcanic ash layers. Particularly the one that's above is dated to around 200 years younger than the suggested date of the Younger Dryas impact event. So that constrains the timing of this meteoric layer that it lies above pretty well. And they've also dated directly from some charcoal. They've dated directly the meteoric layer. And it turns out the date is completely consistent with the Younger Dryas impact, or the suggested date of the Younger Dryas impact. So we can be very confident that this is indeed the Younger Dryas boundary layer here in the edge of this, at the edge of this channel, and they find all the usual indicators of the Younger Dryas impact in this so-called meteoric layer. So they find things like the nanodiamonds, framboidal iron and silica microspherules, and lots of charcoal. And they claim that these are not found in abundance above or below the meteoric layer. So it's pretty clear that we can add this site to the list of other likely Younger Dryas boundary sites. As for the mammoths, it's not clear how the mammoths that are lying in this, or the mammoth bones that are lying in this channel, it's not clear how they met their end. The radiocarbon dating evidence is not precise enough to be sure of whether they were killed by hunters or whether they were killed by the meteoric airburst or by the later volcanic eruption. Okay, so that's a nice paper. We can add that to the list of Younger Dryas black mat sites. Let's move on to the next paper. So this is another paper by the Comet Research Group, and the aim of this paper is to reanalyze the many Younger Dryas black mat sites across the world that have been found to contain nanodiamonds, and to firm up their age depth models. And probably the Comet Research Group here are responding to the several criticisms about the lack of good, accurate age depth models at many of their sites. Now, much of the paper is a response to their critics about how to identify nanodiamonds in the Younger Dryas boundary layer. Remember, this is quite a tricky technical issue. And how these nanodiamonds could have been generated. And of course that they argue for their production via multiple airbursts from comet fragments, for instance, or possibly from a crater forming impact, although an impact crater for the Younger Dryas event is yet to be found. Now, in my view, their arguments concerning the origin of the nanodiamonds are very strong, and as far as I can see, there really is no reasonable alternative process that could have generated these nanodiamonds. So I'm convinced by their arguments. But the main result of this paper is in the supplementary part. Let's just find it. Here it is. And it's a table of these newly generated or enhanced age depth models for the various sites at which the nanodiamonds have been found. Now, in some cases, to generate these new age depth models, they use a technique known as Bayesian statistical modeling. Now, this is the gold standard in archaeological research for generating age depth models, and I think it'd be worth explaining a little bit about what this does. So this Bayesian statistical modeling approach is a little bit different to the usual approach that simply fits a straight line, which is known as linear regression, to a set of radiocarbon data points. Okay, the key difference is that with Bayesian statistical modeling, you define a model of the stratigraphy, in other words, the sequence of layers which contain the items that have been radiocarbon dated. It even allows you to order radiocarbon dated items within a stratigraphic layer if you have good evidence that they must be ordered. And it can even take account of the old wood effect. So this is the effect where a radiocarbon measurement is too old for the event that you're trying to measure, because the charcoal, for instance, that you're measuring is old wood and therefore has a much older date than you would expect. Then once you've defined your stratigraphic model, you can use some off-the-shelf software called Oxcal that will go away, and it'll take your predefined stratigraphic model and the radiocarbon data points into account, and it'll return the most likely chronology for your sediment sequence and all the items that have been radiocarbon dated in it. Now, what this Bayesian statistical modeling approach doesn't do is tell you whether your initial stratigraphic model is correct. It can't do that. your stratigraphic model has to be justified by the archaeological context, such as the sequence of sedimentary layers. So all it can do is give you the most likely dates for all of the items with a radiocarbon measurement, given the stratigraphic model you specify. Now, just to make that a little bit clearer, here is what the software, the kind of thing that the software will do. Now, suppose you have radiocarbon measurements of two different items. So I'm just taking an example here. Let's suppose you've got two pieces of bone from completely different layers in a sedimentary sequence, and therefore suppose you have good reasons to think that one of these bones is younger than the other. So for instance, in this graphic here, let's suppose that this red curve is describing the radiocarbon measurement for an older bone than the blue curve, which is thought to be younger. So these are probability distributions for the age, the radiocarbon age, of each item. This is the older bone, this is the younger bone. And the expected ages are represented by these vertical dashed lines on this age axis here. Now, we know, according to the archaeological context in this example, that this item represented by the red curve is older than this item represented by the blue curve. So it makes no sense then if the actual age of the red item was here and the actual age of the blue item was older here. Okay, that can't be the case if we know that the blue item is younger. So where these distributions overlap, because we know something about the relative ages of these two items, these distributions get modified. And essentially this is what the software, this OXCAL software, does. And so essentially what it'll do is it'll go away and it'll use a sophisticated Monte Carlo technique to modify these distribution curves. And so the red curve will become like this, for instance, and the blue curve would become like this. So where these curves overlap, they are modified essentially. And therefore, because the distributions have been modified, the expected ages will also change. Okay, that's just an example of the kind of thing that this software is doing. It takes into account your prior knowledge of the radiocarbon item, or the items that have been radiocarbon dated. It takes that into account. So in the end, what we're left with is a better set of estimates for the ages of each item. Now, once that's done, the software will also automatically provide an age depth model for the sedimentary sequence based on the modified radiocarbon probability distributions. And it does something similar to what we know. It'll fit a straight line or a curved line to these modified radiocarbon data points. Now, a good example of how this can work is to look at Arlington Canyon. So I've gone back to the review paper by Van Hussel, where they took an average of all the data for the Arlington Canyon site. Now remember, Arlington Canyon this site is located on some islands off the Californian coast, where there's a sedimentary layer about 5 meters thick containing evidence of a comet impact, so nanodiamonds and so on. And the radiocarbon measurements of pieces of charcoal from various depths in this sediment had a wide range of radiocarbon ages. And so taking a straight average of these radiocarbon ages gives an age that is around 200 years older than the suggested age of the Younger Dryas event, which would appear to be a problem. However, we saw previously that the Comet Research Group suggested that the scatter in this data was likely caused by the old wood effect, and therefore the youngest few radiocarbon measurements were probably the better ones from which to estimate the time of the impact event. Alright, well, with this Bayesian statistical method, the Comet Research Group can formalize this suggestion. They can make it rigorous. Their suggestion becomes their model of the stratigraphy, which is justified because apparently it's known that these islands were covered by an ancient conifer forest. And as we know, conifers like the Douglas fir, which were thought to grow on the island, can be huge and very old indeed, perhaps 1,000 years old. So the Comet Research Group, with their modelling, they tell this Bayesian statistical software that there is a single stratigraphic layer, which is about 5 meters deep, and that there is no known order to the charcoal pieces in it. And they ask the software to allow for the old wood effect. And as expected, the software comes back and says, yes, the age of this sedimentary sequence is indeed best estimated by the youngest few radiocarbon measurements, and it takes an average of those. And these other ones are likely affected by the old wood effect. So what have they achieved by doing this? Well, what they have shown is, in a formal way, that is the gold standard in modern archaeological research, they've shown that the Arlington Canyon black mat does have an age compatible with the Younger Dryas impact event, provided, and this is important, provided you allow for the old wood effect. And as we saw, this is justified by the fact that these islands were covered by an ancient pine forest at the time of the event. So that is how this Bayesian statistical modelling works. You define a stratigraphic model, the software goes away, takes your model into account, and returns with the most likely ages of all the items that have been radiocarbon dated. So using this Bayesian approach, and by making some new radiocarbon measurements as well at some of the sites, this is their main result. Let's find it. This table. So what it shows, this table shows, is that we now have many more well-dated black mat sites, or Younger Dryas boundary sites, containing nanodiamonds, whose dates are compatible with the suggested age of the Younger Dryas impact event. As expected, all the sites for which new data were generated, or for which this Bayesian modelling was done, have all turned out to be compatible with the Younger Dryas impact hypothesis. So let's just go through this table in a little more detail. So I've coloured in blue here these sites that use optically stimulated luminescence for dating of the site. Now this is a much less precise method than radiocarbon dating, and so the uncertainties in these age measurements are too large really to be useful for us. So we shouldn't really include these blue, these sites coloured blue in supporting the Younger Dryas impact hypothesis. Likewise, Lake Hind is several hundred years too young. It's an anomalous result, and that site should be looked into more carefully. But if you remember that the date for that site is from a single measurement only, so there could easily be a problem with the measurement at that site. Now the Lommel site is also contentious. The date given in this table here is actually an inferred date. It's not an actual measurement from the site itself. And that was pointed out by Van Hussel et al. So it should be in this subsection of the table, sites with inferred dates. And in any case, the only direct measurement of the site of Lommel was obtained by Wittke in 2013, and we've reviewed that paper already, and that found that according to that measurement, that this site was too old by about 400 years relative to the expected age of the Younger Dryas event. In fact, we can see that data in the paper by Van Hussel. We go back. So here we go. This is the measurement made by Wittke, which is too old by about 400 years compared to the expected age of the Younger Dryas event. So we probably shouldn't include Lommel in our list of confirmed Younger Dryas boundary sites either. Go back to this table. But I think we can probably include this site from Greenland where the nanodiamonds were found, because the oxygen isotope measurements at that site that were made around the nanodiamond layer are matched very well with the onset of the Younger Dryas period. And if we include the new site, which we've just reviewed in this video from Mexico, and if we count up all of these sites, so we have all of the white ones on this section, plus the two independent sites here, plus the one from Greenland and the new one from Mexico, then we have about 15 well-dated sites now, which is a significant improvement on the 7 or 8 or so that we had before. So this is really nice. The Comet Research Group have really improved things here by doubling, essentially, the number of well-dated Younger Dryas boundary sites. And this is just what we would expect, given the platinum spike in the Greenland ice, which strongly suggests it was a cosmic impact that triggered the Younger Dryas cooling. Okay, so that's enough for this video, and we've finally finished with 2014. If you enjoyed that, then please take a look at my book and my blog, and in the next video we'll take a look at papers from 2015.